And would you look at that? We're live. Howdy, everybody. It's the Tuesday night stream. Getting ourselves going here. Getting ourselves going here. Cool. Howdy, howdy. We'll get going here in just a moment. Oh, it's because it hadn't refreshed on my screen. I see. All right. It wouldn't be the night stream without a whole bunch of yawns. We have some stuff to talk about tonight. Some questions came in from a student about optimization problems. I'm excited to work on that. I love optimization problems. For anyone out there who would like to have, if you would like to have your own question answered, I'm so glad you're here. You did come to the right place. My name is Ryan. I'm the calculus tutor. I'm here to answer your math questions. I assume for a lot of you, that's probably questions from math class, probably about math assignments or topics you're being quizzed or tested on. That's what I expect. Most of the questions here will probably be for send them in. But also, if you have questions just from your everyday life, feel free to send those in. If you think getting sort of a mathematical understanding of a problem you're trying to actually solve, or just a problem you're interested in, if you think a mathematical perspective could be helpful, send it in. We'll turn around, talk about it, see what sort of solutions math can come up with. So if you would like to submit a question, here's what you're going to do. You're going to go to thecalculustutor.com. And if you go to thecalculustutor.com, this is what you'll see. Excellent. When you scroll down, you can watch the stream here. Submit a question right there. Boom. So you'll click that button. It'll navigate you to the stream page of my website. And scroll you right on down to the submit homework problems section. And you can click this homework submission form and go there and submit a homework problem. You can also just email any questions to ryan@thecalculustutor.com. If that feels more straightforward or easier for you, absolutely feel free to do that. And we'll talk about how to do that in just a second, but let's see what happens when you click. It should take you to submit your homework questions below. Now, it may, before you see the form itself, it may ask you to sign in to a Google account. And that's because you can submit photos, images through this form. So you can submit images of the problems you're working on. And if you do that, Google requires that the people that submit the form be signed into a Google account. I think I appreciate that ultimately. Anyway, feel free to just sign in with your school Google account if that's the main one you use, or your personal Google account, whatever. If you do sign into your school Google account and then you sign in and it doesn't take you to the form, try to go back to the website, click the button again. But if it's popping up a message that says you don't have access to this form, it's because your school or your district has your Google accounts locked down in such a way that you can't access stuff outside of them. Send me your question via email instead. That's part of why I have the email set up that way. But if you do, please mention that you tried the form and it blocked you, and just tell me what school district you're with. I'll try to reach out to them, see if there's anything we can do to make it so people can access the form. But regardless, everything I go through on this form, that would be a great thing for you to include in your email as well. So I've set up this form so that people can submit good questions easily so that I can give good answers. So let's go through this. What does it take to submit a question? I want it to be as simple as possible while still needing it to be thorough and robust, right? So let's see what this is. So you just have to check that, yes, this is your Google account and that you're submitting this form with it. Tell me who you are, and this doesn't have to be like your real legal name. This is just whatever you prefer for me, however you prefer for me to refer to you when I'm answering your question, right? Because I'm going to go and be like, oh, this question was submitted by such and such. Who is such and such for you? And that way you also can listen for when I'm answering your specific question. You can include your pronouns here. This would be a good place to include your pronouns if you care. Otherwise, I'll probably just use they. Next section, where did this question come from? This is just really quick. like I said at the beginning, most people submitting questions are probably submitting like homework or like test review questions, that sort of thing. So just tell me the teacher and the class, right? Mix Smith's Algebra 2, Mr. Jacobson's Geostats. That's it. If it's not from a class, tell me where it's from. Where in your life did it pop up? Again, one sentence max. Tell me more if you want, but like, this is not meant to be a barrier. It's just a quick organizational thing for me. And as I'm going through looking at the questions, if I see one that like is not from a teacher and a class, I'll be like, oh, and I can like be, oh, this is from somebody's life. But yeah, so that just helps give me some context, and it will help me organize answers that are on homework problems and stuff like that. Because eventually, I imagine I will get the similar or say the same questions here and there a few times. It'll be nice if people can just look up and see if I've already answered questions. All right, so all that's out of the way. The main thing here is, what is your question? The goal here: be as specific as possible. But again, it's not meant to be a barrier. So I don't want you to have to retype the entire math question, right? That'd be such a pain in the butt. It wouldn't. I feel like for a lot of students, it wouldn't even be worth submitting a question. So when I say be as specific as possible, keep in mind you are going to be able to attach an image of your problem. So you don't need to actually describe the what the problem's asking you to do. What this box here is for you to tell me. So you send in a picture of like your worksheet or your textbook page with all your problems, right? And you tell me, um, number 18. But that's not enough. Like, that will help me see which problem you want me to work on. But like, your question is you probably are struggling with something more specific. So, you might tell me number 18. Um, uh, I don't, oops, wow. Oh my goodness. I'm typing so sloppy today. I don't know how to factor the quadratic. And now that might seem actually a little vague or whatever. And obviously, I'm just making things up here. But as I look at the problem and as I work through the problem, I would probably be able to understand what you meant by the quadratic. Like, there's probably a quadratic that is prominent in the problem, either from the very beginning or partway through, that's giving you trouble. So that's like a way to be really specific. But sometimes, you know, I don't know how to factor the quadratic, or it could be something like, the problems we did in class didn't have fractions. Right? And now you send this in, and I see, oh, this tells me a couple of things. It tells me, one, you have worked on problems like this in class and you recognize that. But two, that these problems feature fractions in such a way that it's throwing you off. And this also sort of tells me a little bit that you probably would feel more confident with the problem if it didn't have the fractions. Like, you might not even have sent in the problem. Um, and that's really informative to me. That helps let me know that uh, it might be worthwhile to spend a minute after we go through the problem reviewing fraction stuff, right? If there's not another question immediately to answer or something like that, a little review of fraction and fraction arithmetic could be worthwhile. Yeah. Sometimes though, it's not even. You're not even sure. You're like, sometimes it's I don't. Oops. I don't even know how to start. Um, some people might think that is kind of a cop out sort of a thing. I don't think so. If that truly is what's happening here, you're like you're like you really have that like I don't even know where to start feeling, and I understand that feeling a ton. Um, that's actually really useful to me. We can talk about how do you start these problems. Right. So this part right here, notice none of these things that I put down was longer than one sentence. So like one or two sentences is all you need here. Tell me what problem to focus on. Um, and tell me what about that problem is giving you trouble. Maybe you're like, oh, I got through parts A and B just fine. Part C requires graphing, and I'm not sure how to graph this. That's great. That means I don't have to spend as much time on parts A and B. I can sort of check in on them really quick and then run us into part C and really focus in on that graphing. All right, so that's that part. We'll come back to this section right here and now attaching images. So the main thing here is for you to be able to, if it's a worksheet or a page in your textbook, for you just to be able to snap a picture really quick. The key with the pictures is to be clear and complete. Clear just means I can read the text and all of the relevant numbers and things like that. If I can't, and now I'll try to meet you part way. It can be hard to take a picture of a textbook page where literally all of the text is in focus. That's just kind of not how cameras and phones kind of work sometimes. Um, so I'll do my best. If it's a little blurry, I'll still probably be able to read it, but double check it, make sure it's legible. Um, the other thing, so that's clear. Complete means make sure you don't accidentally crop off part of the problem when you're taking the picture. Uh, that's kind of the most obvious part. But the other thing is, a lot of times the problem you're working on, like worksheets and textbook and stuff, they have the instructions for the group of problems you're working on are sometimes separate from those problems, right? Like the instructions are down here, you have a couple of problems, then you have a couple more problems up here. So if you take a picture up there of your problem and it doesn't include that block of instructions, make sure you just also take a separate picture of the instructions and also send that along. You can attach up to 5 images here. In addition to instructions, also make sure your picture includes, or you take a separate picture and include it, of any diagrams or figures or charts. Uh, Honestly, this includes like even if you're given a blank coordinate axis to graph on, or a blank number line, or anything, whatever, a blank chart or table to fill out. Um, if your picture includes that, I will use that in my notes. So I'm working on the problem in exactly the same way you were meant to work on it. So including that stuff can also be really helpful. The final thing that you might include here is if you've already done some work on this problem and you got stuck partway through, or you did a similar problem already, like you did number 16 and you're asking a question about number 18. Um, or you did problems like that in class and you have notes, sending me a picture of any work you yourself have already done related to that particular problem. So if you've already done work on that specific problem, go ahead and send that in. If you haven't done anything yet, but you've done work on a similar one, like I said, whatever seems the most relevant. You don't have to send me all of your notes. I don't really want them. But if you send me a good picture of something relevant that you've done, that can actually be really helpful to me to see if maybe there's something in there that indicates you have a misunderstanding, or maybe something wasn't fully explained or explained at all, right? And so you're using a notation or a math thing uh, that was just never really explained. Um, yeah, my promise to you is if you send me a picture of any of your own work, that will not show up on stream. Um, Yeah, you're sending that to me for me to help me answer your question and address really as best I can the thing that's making that problem so difficult for you, most difficult for you, because usually there's some bigger underlying thing. Sometimes you just want to see how a problem worked out, and that's totally fine, right? So you're under no obligation to send me a picture of your work. And honestly, if all you want is to see somebody work through the problem, so you just send me a picture of the problem, which number, and say, I'd like you to just work this one through, and that's all you send me, that's great. I'll still work through it. I just won't know what parts of the problem to focus on. So I'll address what I would assume are common pitfalls and things like that. Um, Now you may have noticed there is a place where you can tell me that I can share your work on stream. My thinking here is another thing you can do rather than just submit a question, a problem you have a question about, you want to see me work through. Another great way to use this time and my availability here is to send in your work and have me check it for you. This could be particularly important for like assignments that are a big deal, or if you're doing like a test review, and so your teacher gave you a bunch of practice problems, um, and maybe your teacher even gave you the answers, but not the solutions, not the steps, right? And you're like, yeah, I got some of these right, some of my I figured out how to get right, but like, can you just like check my not just your answers, but check your work, right? Honestly, this is going to be most helpful for students in like pre-calc, calculus, and like potentially like university and college students. But I wanted to put something there because for some students, the thing that would actually be really useful to them is if I did go through their work and say, "Oh, this looks great. Oh, watch yourself right here. I see exactly where you went wrong," or "Oh, this is a common thing to do." Um, "Oh, I see you sort of cross multiplied here. Don't ever cross multiply. Cross multiplication is a scam. Do it this way instead." Um, that sort of stuff. Um, and I can't do that without showing, or I can't do that as effectively or as easily, mostly, I think is what it is, without being able to show your work on stream. So um, I included that option there for the requests that I actually go through people's work. That's what they would like from this. Actually, that's what would be valuable is if I went through their work. So yeah, feel free to send in your work on any problems um, uh, that you've already done, but you'd like a like kind of like an art critique, but over your math process. That'd be fine with me. So yeah, that's the form. Now, um, if for whatever reason your school Google account is blocking you from accessing the form, or you just don't want to use it, or you really feel like you need to send more than 5 problems, ooh, really quick, that form also lets you submit PDFs. So if you have like a PDF packet, you don't even have to take a screenshot or anything and attach it. You can just send the whole PDF. Just download it, send the whole PDF along to me. You have to be specific about where in that PDF I need to go to get to your question, um, but also, yeah, if you have like web work or my open math or can questions in Canvas or whatever, um, just take a screenshot and attach that. That should be fine. Um, but yeah, so but if the form's not working for you for whatever reason, or you'd prefer just to email me, this section right here. So here's the email address, Ryan at thecalculustutor.com. I guess I could set this up to insert a subject like um, math homework help stream question or whatever. Uh, just put math question or math or whatever in the. You can just leave no subject in the subject too if you want. Um, I'd prefer if you put something like math stream or math question, but anyway, here's what to include in your email. It's all the same stuff that I just went through on the form, but here it is spelled out because when you send an email, there's no prompts. It's just it's just a blank canvas, and you have to figure everything out for yourself. But no, you don't. Here, I figured it out for you. Uh, it's all the same stuff. Include your name. That's just however you want me to refer to you when I'm answering your questions, including pronouns if you care. Your problem source, teacher, and class, or where from your life the problem came from. Your specific question, right? So be just a little bit specific about what about the problems giving you trouble. And then, of course, you can attach your image. Yeah, you can attach images to an email. So just make sure those images are clear and complete, like we talked about before. And there it is. That is the math homework help stream. And then I will answer your questions. Um, well, stream is actually started now. Um, I will answer your questions here. So I guess and so this is great. You can, I'll work on stuff, but this will the screen will just follow me, but maybe you need me to go back, or maybe you need to look at the stuff that's back earlier. So here's what you can do. Oh my God, there it goes. So there's the notes that just flashed on screen. Sorry about that. We'll go back to the notes in a minute. I forgot to mention, and you may have noticed though. So in order to access the notes, so you can just access them whenever you want, or so you can scroll around freely within the notes. Back on the website, just in the pink stream box, there's a Go to Notes button right there. There's also up here under the Math Live Streams header, there's a Math Notes. Those go to the same place. And then, of course, back on the home page on the stream box, there is a Go to Notes button right there as well. And those notes, or those buttons, those links, will take you specifically to these notes. And so you can follow along, or you can go back if I've gone past the section you were looking at. Granted, feel free to hop into the chat and ask clarifying questions while I'm going through your question, or if you're watching as I go through somebody else's, also feel free to pop in clarifying questions if you're following along with somebody else's question. So yes, you can always ask me to slow down or repeat a thing or explain it again or whatever. But I know it will be useful for you to be able to navigate the notes on your own. So those buttons are how you get there. And that just lets you navigate this entire document on your own. And if you want to, though, if you're navigating, but you're like, oh shoot, where was Ryan? I want to see what they're working on. You can just click on my picture in the upper right hand corner, and that will jump you straight to me. So yeah, this is the Homework Help Math stream. That's how you. Excuse me. Sorry. That's how you submit questions. That's how you access the space where the at least the text written component of my answers and to your questions will be. We do have here. Well, first of all, let me double check the form and my inbox. Okay. So, no questions. Well, kind of questions. One of the students I work with one-on-one, a calculus student, is working on optimization problems. And so no, okay. Oh, excellent. Okay. We'll just do that. There we go. I kind of like how these take up pretty much the whole space. Makes it very clear where the sort of problem divisions are in the document. Okay, so optimization problems. Actually, I'm gonna try to practice this. I'm about to answer this question, so I want to add a stream marker. I don't know what that does, but it says it'll appear in the video editor. Okay, so optimization problems are about finding the most or the least of something typically, or something that fits a criteria the most. And sometimes that means by being the least, right? If you want to, if you want to them to minimize cost, well, your criteria is the least of something. Um, Calculus offers us a nice way to do this because the derivative, when the derivative is zero, we know that's a place where a local min or max might be. And so by taking the derivative and setting it equal to zero, we can often find these optimizations. We also, so that's optimization in general. What calculus can make really useful is this idea of constrained optimization. So let's get in here. Let's see what this problem actually is. I don't know where in the optimization sort of spectrum this will be. So let's just look at this. An open box is to be made out of an 8-inch by 18-inch piece of cardboard by cutting out squares of equal size from the four corners and bending up the sides. Find the dimensions of the resulting box that has the largest volume. Give your answers to at least 2 decimal places. Okay, so oftentimes with problems like this, optimization problems, honestly, pretty much any real applied problem or word problem, right? Make a diagram. So here's what we're going to do. I'm going to make myself a little diagram. It is 8 inches by 18 inches, so it's pretty thin and long relatively. Here, I'm going to make it actually, oops. I'm going to make it a little bit bigger just so we have a little bit more to work with. Okay, there's that. But then it also has cut out of the corner. And here we're going to make these dashed. So it has these little squares cut out of the corners. And now what that does is it creates these little tabs that are sticking out on the top, bottom, left, and right. Okay, so let's get those all in place. Okay, so here's our diagram. Let's label it. This distance here is what, 8 inches is our unit. So this is 8 inches. This distance here is 18. Oops. Let's make that legible, shall we? 18 inches. And then I'm going to call, these are little squares. It says 8-inch by 18-inch piece of cardboard, cutting out squares of equal size from the four corners and bending up the sides. So, dot, 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 dot. So these little things are what are, these little tabs right here are what are being bent up. Oops. There we go. And in fact, you know what we could do? So these squares are not here. They've been cut out, right? So they're gone. And all that we're left with are these tabs here, right? So we'll fold this up, we'll fold that up, we'll fold that up. And what we'll be left with So we'll fold it. Oops. And what we'll be left with is an open-topped box. Like that, right? And so the whole side of the paper, or the cardboard, the piece of cardboard, is 8 inches and the length is 18 inches, but we're going to lose some of that when we fold up these panels. How much are we going to lose? Well, they don't say how wide the squares are because we get to decide that. However big the squares are that we cut out, that's going to determine how much is lost from each side. In fact, it'll be 2 times that, right? Because we lose x here and we lose x here. We lose x from the top and we lose x from the bottom. And so, but x, that is this distance. So the height is x. The width is 8 minus 2x. And the length here is 18 minus 2x. Yeah? So we want the box with the largest possible volume from this sheet, right? Because if we cut off just little tiny squares, it wouldn't have a ton of height. And while it would be as wide and as long as possible, it wouldn't have hardly any height. And so it wouldn't hold any, it wouldn't have much volume. Think of how much, if we were sealing the corners and all that stuff, if it was watertight, think of how much water it would hold. A little shallow thing is not going to hold much water. You want to make it deeper. And certainly you're going to squash it in from both dimensions, right? And so it won't be as wide and it won't be as long, but it'll be deeper. And so what's going to happen is you will, for a while, as you make it deeper, even though you're making it smaller in the other dimensions, it will hold more and more water until you get to a certain point. And then at a certain point, if you keep making it deeper, now you're losing too much width and length, and it will start holding less. So there's a perfect size to make those cutouts so that the resultant box has the largest possible volume, would hold the most possible water. And that's what we're looking for. That's the optimization of this problem. Okay, so we have a handle on the shape of the problem, as I like to think of it, right? We know what the problem looks like. We sort of know logically what we're going to accomplish here. So now we need to sort of mathematically figure out how we're going to tackle this. So whenever you have one of these optimization problems, you have to look for what is the optimization quantity? What quantity are we trying to optimize? So you find the dimensions of the resulting box that has the largest volume. We want to optimize the volume of the box. Oops. Of that box. Cool. So what's the volume of a box? Well, the volume of a box is just length times width times height. So what's the volume of that box then? Well, its length is 18 minus 2x. Its width is 8 minus 2x. And its height is just merely x. Excellent. That is the volume for this particular box. As a function merely of the size of the squares we cut out of it. This is exactly the equation we need. And so we could just plug in a bunch of different values of x, plug in 1, plug in 2, plug in 3, plug in 4. and put them in a chart and then just see which one gives us the biggest volume. That would be sort of the clunky, brute forcey way to do it, the sort of inelegant, non-calculus way to do it. We could totally do it that way. And then even if the true value of x isn't a whole number, we just find the whole number that gives us the biggest value. And let's say it's 5. I don't know if it's 5. I don't think it will be, but let's say it's 5. 5 is the whole number that gives us the biggest volume. Then we try 5.5 and 4.5 and see see if either of those give us a bigger volume. And if one of them does, we know, oh, the true value of x that's not a whole number is on that side of, say, 5. The whole number that we found was the biggest whole number. And so there'd be ways to do this without calculus at all. But calculus is going to give us a pretty direct path there. So now that we want, so now we know we want to find the maximum value of this function, of this volume function. All right, so the maximum is where the derivative is equal to 0. To take the derivative of this, right, we have 3 things being multiplied. We'd have to do like this kind of 3-way product rule, which we could totally do and could be worth talking about, is like, how do you deal with a product rule when you have 3 things being multiplied? I think that's actually overkill, though, because here's the thing. This is going to multiply out to be a really regular polynomial. Granted, the number is going to be kind of wonky. We're going to have to do an 18 times 8 in here at some point. But that's just a multiplication. We can do it. We can use a calculator or whatever. So first, let's multiply it out to make finding v prime of x easier. Okay. So we're going to do, we have x times how do I want to do this, actually? It could be worthwhile to factor out the factor of 2. So, no, I think that's going to be confusing to follow. So we'll just multiply it out. So let me write it out really quick. Okay. So we're going to multiply these 2 binomials first, and then we'll deal with this x at the end. Because if we multiply the x in first, it's just going to make one of these more complicated than it already is and make the subsequent multiplication a bigger pain than it needs to be. Whereas at the end, it'll be super easy to just multiply in this single x. Okay, so let's do this. So we're going to do 18 times 8 and 18 times 2x. So we're going to get x times 18 times 8. 10 times 8 is 80. 8 times 8 is 64. 80 plus 64 is 144. 18 times 8 is the same as 12 times 12. Wonder why that is. And then 18 times negative 2x. Negative 2x is negative 36x. All right. And then we also want to do, so we've done the 18 times both of these. So now we want to do this negative 2x. Remember the negative times 8 and negative 2x times negative 2x. So negative 2x times 8 is negative 16x. Negative 2x times negative 2x is positive 4x squared, like such. There we go. I'll go ahead and combine these really quick. So we'll get x. I'm also going to turn this around in the process. 4x squared, 30, -36 minus 16 is going to be -52 plus 144. I'm just going to make a note here that that's what I did from my student looks back at this. Combine like terms, reorder terms. So those are two things I just did there. We will now look at this. We'll take voop, voop, and voop, multiply that there. But it's just an x, so it becomes 4x cubed minus 52x squared plus 144x. All right. So this is v of x. There we go. V of x equals v of x equals v of x equals. I'm just going back in to fill that in for completeness. All right. Max of v of x is where v prime of x equals 0. So v prime of x, so we'll go through here, bring the 3 down, multiply the 4, and you get 12. X, reduce the exponent by 1 to get a 2. That's our power rule. Then here, bring the 2 down to multiply -152, and you get -104. And then take the 2, reduce it by 1, so you get x to the first, so I'll just write it as x. 144x, so we can think of this a couple ways. What I like to do, this is a 1 exponent. 144 times 1 is 144. 1 minus 1 is 0, so this is x to the 0, and anything to the 0th power is just 1. So 144 times 1 is 144. And that's that derivative. Very quickly, we're not right at this moment, we're not focused on those derivative rules, but we can focus on them at some point. So we have our derivative now. Now we just want to set it equal to 0. All right, we have 0 equal to quadratic. Pretty straightforward thing to solve. Remember, with quadratics, you can always use the quadratic formula, and it always works. That's a very sort of calculator-intensive way to do it. If we want, we might be able to factor this. So if we were going to try to solve this by hand, first thing we would do, even if we're going to plug into the quadratic formula, it's nicer to pull out large factors. So what's a number that divides both 12, 104, and 144? Well, I know 4 does. Does 6? 6 doesn't. 8 doesn't. 12 doesn't. Because there's 40. Yeah. So I think 4 is the biggest number. So first of all, we're just going to factor out that 4. And so this is going to be 3x squared minus 26x plus 36. Oops. I'm double checking my, yeah, 36. Okay. And now this 4, Now, if we had factored out a variable with this, if there had been an x that these also had in common and this was like a 4x out here, we wouldn't want to just divide this over because we'd lose that variable. It would just disappear when we divided it into the 0. But because this is just a 4, it's just a constant, we can totally right now, we can just say, boop, by 4, boom. It's not contributing anything to the values of these x's because, right, the only way 4 times all of this stuff can equal 0 is if either 4 is equal to 0, which it never is, or if all of this stuff is equal to 0. So we'll just do this and have a slightly simpler equation to deal with. So let's just boo, boo, boo. So we'll say factor out and divide away GCF of 4. All right, so that's why we pull out a 4. That's the greatest common factor of all of these. Pull it out. All right. Now, to factor this, you know what? That's not what we're focused on here. I actually want to talk about factoring tomorrow. I was gonna talk about factoring tomorrow, as a matter of fact. Um, so for now, we're just gonna say multiple ways to solve. I recommend quadratic formula. All right, so our quadratic formula, I think I actually have a little thing that I'm just going to paste in here because I've already made it. If it'll load. Sorry, y'all. Computer's going a little bit slow on me. Here we go. Boom. This is what I was looking for. Aha. I know how I'll. Here we go. I'm just trying to get something into the Miro board, something I've already made. So rather than remake it right now, I'm being a little lazy and grabbing it from a different board. Boom. I recommend the quadratic formula. Right, so here's our quadratic formula. And so we can say x must equal the negative of b, so negative 26 plus or minus the square root of negative 26 squared minus 4 times 3 times 30 6, boom, all over 2 times 3. And now we can just follow this through. This is 26 plus or minus the square root of 26 squared is 676 minus 12 times 36 is 432 all over 6. 26 plus or minus square root, boom. 676 minus 432 to 44. Which doesn't have a nice square root, I don't believe, which means this actually would not have factored anyway. Right, so this is why I recommend the quadratic formula. Not every quadratic is going to factor, and if they're simple enough, you can just look at them and say that doesn't factor. But something like this, I thought maybe it might. The numbers look straightforward enough. Yeah, so square root 244. Yeah, that's a little bit more. That's a little bit over 15 and a half. So this never would have factored, is what that tells us. Which means quadratic formula is just, and you could also graph it. You could use Desmos to just straight up graph it and find the but if you're going to graph it, we could have just graphed the original volume formula and used Desmos to find the top of the graph. And in fact, that could be a worthwhile thing to talk about if we still have some time after I answer some of these other questions. Anyway, here's this problem. Let's keep going. So I'm gonna, now that I know that it's just a decimal, I'm gonna go ahead and skip ahead. Right, and so we'll say boom, boom. X is approximately, here, we're gonna do square root, no, I need to do, what is it, 26? Plus square root 244 over 6. There we go. But also we do that, and then we change it to minus. Oops, wrong button. Here's that. Here's me calculating that. Oh, that's smaller than I wanted it to be. Here, we'll put that there. Boom, boom, boom. And so that tells us X is approximately 6.9. And actually, I think it even told us how many decimal places, but it's WebWorks, so I would imagine it says at least 2 decimal places. The height of the box is going to be the X value. I would recommend you just put full calculations in here. So whatever you type into the calculator, just put it in here instead. So whichever one of these gives us the largest volume. So here's what we do. Here's how we figured out. Which is the max? Whichever gives the largest v of x value. So we will now do v of 1.73-ish and we'll do V of 6 point, this is 6.94-ish. But here's what I'm going to do. So we go back to our original volume formula because we just want the maximum volume. Because this is a polynomial, it's continuous. It doesn't have any jumps or weird behavior or gaps or anything like that. We know its maximum has to be it has to be at a place where it goes to a local max. And so those can only happen when at places where the derivative equals 0. We found the only places where the derivative is equal to 0. Which means, actually, you know what? I just realized we don't have to plug these in. There's a more logical way to look at this. I am so sorry. So here's what we're going to do. I'm going to get, I'm just going to get rid of all of this. And we can look at these numbers, though. And we can say, this number right here is too, here, I'll do the arrow in just a second, too large. This is bigger than half the 8-inch width. So this cannot be the max. The max must be x equals approximately 1.73 inches. So we can go back up to the top and we can say, so I'm scrolling around a bunch, sorry, let me zoom out. The 1.73 inches, that was when we had minus in here, 26 minus that square root. So that's what we're going to input in here. We're going to call this 26 minus the square root of 244 all over 6. That will make sure WebWork calculates it out to as many decimal places as it actually wants. Sometimes these problems say 2 decimal places and it actually wants 6. WebWork can be wonky. Then the dimensions of the box. Find the dimensions of the resulting box as largest volume. So because it gives the dimensions as the short dimension, then the long dimension, we're going to do ours in the same order. It might be smart enough to not care what order you put them in, but it doesn't tell us explicitly, so we have to find some way to figure it out. So I'm going to do the short dimension first, which is just 8 minus 2 times this thing right here, 26 minus the square root of 244, 244 over 6, like that. That's how I would input it. And then it's just going to calculate it for you. And same thing over here, 18 minus 2 times, and then 26 minus root 244 all over 6. And there we go. Now, here's the thing. How do we know for sure that that's the largest volume? We can, here's, what do I want to do here? I want to go to Miro, and I want to be able to share my screen. But actually what I want is to put a graph in here. So actually, I'll just, okay. So I'm trying to figure out which screen to do things on to most easily share them with you all. So give me 1 second to go to Desmos and get a graph going. So here's what I'm going to do. I'm going to graph the volume formula, right? Uh, so our volume formula was x times 8 minus 2x times 18 minus 2x. And then we multiply that out into a cubic. Now, some of you that remember your graphing from like algebra 2, I guess, uh, might remember what a cubic looks like, right? Like it's going to go, typically it's going to go up and then down and then back up. So its maximum is going to be on the left typically. And so here, so I just graph this. So we should expect the graph to look like that. Oh yeah, let me make this. This is great. This will give me a chance to adjust this. So x-axis. We don't need to go below 0. I'm going to go down to -5 just to give us some space on that side. X couldn't possibly be larger than 4 because if x was anything larger than 4, that would be more than half the 8-inch width of the box, right? And so we would those X panels would overlap. You wouldn't be able to do it. You physically can't get a X to be bigger than 4 if the sheet of cardboard is only 8 inches wide. So our x-axis doesn't need to be very big. And now our volume, did I ever actually calculate the actual volume? I never did. But x is less than 2, so it's going to be like something a little bit more than 6 times something a little bit more than 16. Can I enter math in this? It's definitely not going to be less than 0. So if I do 2 times 16 times 6. Oh, you totally can do math in here. That's awesome. Okay. Okay. I think this is a sufficient graph. So the graphing that I'm doing right here, this is not an essential part of the problem. I am trying to justify why we don't need to do all of the rigmarole of doing like a second derivative test to see if this is a maximum or plug in test points between this one and the other one to see if this is a maximum. We don't have to do any of that stuff. All of that stuff is theoretical and it's like how you would prove that something is a max. But what's really great about real life is there are restrictions on reality that mathematics doesn't have to obey. So for example, the fact that x could not be larger than 4, well, we found one of our solutions, right? One of the x values we found was 7 point something or 6 point something, almost 7, right? Um, and so the math isn't aware that this equation had to do with a physical piece of cardboard that had constrained dimensions. We encoded that in the math, but we understood what it represented. There's no way for the algebra or the calculus to understand it. That's what we're for. That's the power of us doing the math. Um, oh, here, let me grab the equation too, just for completeness. There we go. Boom. Okay. Link those together. Boom. Okay. So there's our equation. There's our volume equation. And as you can see, it is that classic up and then down and then back up. Granted, I cut off the bottom because, again, that's below y equals 0. Remember, y in this case is the volume. So any dimensions here that give us a volume less than 0, are irrelevant. Those are artifacts of the math. They don't reflect the real life context that we're dealing with here. So yeah, I wanted to show you that this right here is a perfectly valid way to have solved this problem without calculus. Um, Desmos will tell you exactly what this point right there is. I didn't have it tell me, but it would tell you exactly what it is. But look where it is. It's here's 1.5, here's 2, here's 1.75, and here's our dot right here, just a little bit to the right of 1.75. Um, oh, no, I'm sorry. This is 1.5. This is 1.5. 1.75 would be like right here. So we're just almost in the middle, and that makes sense. 1.73. Very good. We can see 4 here. It's going back through 0 because if you make it 4, it splits the piece of cardboard in half, so your volume would be 0. You couldn't get any water in that. So yeah, there we go. I guess actually I want to make this green. Here's our point there, green. So I just wanted to show that because we understand the reality of the situation and we understand some of the behavior of the functions that we're dealing with, in this case, a cubic, and we know how cubics are shaped, even though we could go through the process of plugging in test points into the derivative just to make sure it's increasing on the left and then decreasing on the right, right? The shape of a maximum. We could do all of that, but we don't need to. It's overkill for this problem. And that's a really important part of math. Not just doing math because it's the process that you memorized, right? Doing too much math, doing more math than you need to, it doesn't help you learn the math, doesn't bring anything to the problem. So anyway, I just wanted to demonstrate that. So here we are. Here's our maximum. So I am going to bind all of this together. Boop. And that way, none of it can, oh, and in fact, let's lock it so I can't mess it up. There we go. So now that's locked. Really quick, now that we're in between problems here, I'm getting overly warm, so I have long sleeves on. I'm gonna change into a t-shirt. So give me a moment. I'll be right back. Boop. All right, y'all. We're back. Hair's all crazy. We have a bit of time left. Let's see if we can't get through another problem or two. Let's see this right here. All right. Let's get back here, shall we? Oh man, I have a sneeze coming on, y'all. Goodness. All right. A fence is to be built to enclose a rectangular area of 260 square feet. The fence along 3 sides is to be made of material that costs $4 per foot. And the material for the 4th side costs $13 per foot. Find the dimensions of the enclosure that is most economical to construct. That's just cheapest. Least. Okay, yeah. Oh, I should mark this in the thing. Hold on a sec. Here we go. Add stream marker. Yay, I did it. I'm being a good streamer. Okay. Fence is to be built to enclose a rectangular area of 260 square feet. So we'll mark some of this given information. The fence along 3 sides is to be made of material that costs $4 per foot. And the 4th side, $13 per foot. So it has like a front facing side or something, a side that faces a road. So it's a nicer fence or whatever. It doesn't matter why. But this is somewhat realistic, right? Not every side of an enclosure is going to cost the same amount. You might have different needs. Okay. Again, great place to start is to sketch, right? And so we're going to do, here's actually what I'm going to do. I go back here. We're going to underline this. There we go. And then this right here, that's going to be, I don't know, that's going to be a bright green for us. Okay, everything's a little bit, so along the 4th side, there we go. And then we have 3 other sides. Oh my gosh. Boom, there we go. And so this enclosure has a length and it has a width. That's what I'm going to call those dimensions. We also know that the internal area is 260 square feet. Right, so we know that's the area. We know that's the relationship between L and W. So right off the bat, we can say L times W equals 260. This is what we would call our constraint. Because this is a constraint because the most economical enclosure to build would be one of 0 size because it would cost 0. But we are constrained by having to build one that has an area of 260 square feet and nothing smaller or larger, though to build one larger would necessarily mean using more materials and therefore would be more expensive, I mean. Okay, so this is what's called our constraint equation, and the constraint equation relates the otherwise unrelated variables of your situation. What do we want to optimize? So this is our constraint equation. Now we want to know what we want to optimize, our optimization equation. We want to optimize cost. So we're going to call that, actually, because there's not a lot of reasons for this, but because the length is the one that has the special cost rather than the width, and the width doesn't care about the additional special cost, the more expensive cost. So I wanna, well, actually, here's what we do. Cost as a function of length and width. There we go. So I won't even write it that way. We'll just say optimize cost. Cost is equal to, so we know we have 2 widths, and each of those widths are going to cost $4 per foot. We also know we have a length that is going to cost $4 per foot, and we have another length that is going to cost 13. I crammed those in there. I do apologize. Let's bring those out a little bit, shall we? Plus a length that is going to cost 13. So what is this? This is both widths cost $4. One length costs $4 per foot. And then one length costs $13 per foot. So we're going to get C, or cost, is equal to 8W plus 17L. And we can sort of see the sense in this, right? Whatever the width is, it's actually going to cost $8 per foot because you have to do two widths, 2 distances. So even though each one separately costs $4 per foot, because there's always, for every foot you place on the right, you're going to have to place a foot on the left. So the width actually costs $8. The length ends up costing $17 because for the bottom, for any foot on the bottom, that's going to cost 4. And for that same foot on the top, it's going to cost 13. So for a total of 17 feet. And so that's sort of what this equation, when we reduce this equation, we can extract some information. The problem's not asking us for this, but it's interesting to be able to read these equations and understand as you take steps, that information means something. There's often a way to interpret those new numbers that you get. They mean something else about the problem. Okay, this is great. However, what's tough about this is this has 2 different variables. So how do we minimize it, right? This has This has two variables. How do we optimize? The answer is use the constraint to substitute. Boom. So if we know W times L equals, what does it equal? 260. Well, we can, let's divide by L. And we get that W is equal to 260 L. So now we can substitute that. So for the cost function, 8W plus 17L. Well, now we can take this and plug it in right there. And we get 8 times 260 over L plus 17 times L, like that. We'll go ahead and do this multiplication. This is 8 over 1, so the 8 times 260, I don't even. Eight times 260, 2080. So this is going to be 2080 over L plus 17 times L. Now, here, I'm not really sure what that 2080 actually represents in this problem. We could probably, we can interpret this 260 per L, right? That this is just W, right? So at this point, because we've done the substitution, we sort of obscured some of the meaning, but that's totally okay, because now look what we have. We have a C of L function. Let me write this more clearly. C of L. We have a function. Now we only have one variable, right? And if we hadn't had that constraint equation, we wouldn't have been able to do this. Now, granted, we might have been able to come up with some other substitution that let us figure out some relationship between L and W, but oftentimes that's what your constraint does for you, is it gives you a relationship between the various, at least some of the variables in your problem. And because there's that relationship, if you know one of those variables, you have to know the other. Because we know the area is going to be 260, as soon as we figure out the length, we just do 260 divided by L, and boom, we instantly have the width, just like we did the substitution, right? So we're sort of like pivoting around the constraint to allow us to simplify the optimization equation into one variable, one input variable at least. Have one variable. We want to find the minimum and in fact, let's make this green because this is our goal. This is what we're trying to achieve here. We want to find the minimum of C of L. So find C prime of L, set it equal to 0, and solve. All right. C prime of L here. Um, First, actually really quick. Actually, I'll just rewrite it. Yeah. First as 2080 times L to the negative 1. All right. Whenever you have variables in your denominator, and you're trying to take derivatives, just move them up to the numerator and make the exponents negative. It's just going to make everything so much easier. It means you can use the power rule. All right. So we have C of L, of L is equal to 2080. Let me make sure I'm not dropping any numbers here or anything. Yeah, 2080 times L to the negative 1, right? Same thing as 2080 over L plus 17L. That is our equation. Okay. Now, C prime of L, the derivative, right? So we bring the exponent down, negative 2080 times L, and we subtract 1. So negative 1 minus 1 is negative 2. Here, this is L to the first, so we bring 1 down. 17 times 1 is 17. This is a 1. 1 minus 1 is 0. L to the 0, anything to the 0 is 1. So 17 times 1 is just 17. And here it is. This is our derivative function. I'm going to go ahead and rewrite this as negative 2080 over L squared plus 17. Now that I've taken the derivative, I'm going to rewrite that negative exponent, put it back in the denominator. And that's because it might seem silly to keep moving it back and forth. It's easier to deal with exponents that aren't in the denominator when you're taking a derivative. But then when you're doing algebra, at least for me, it's easier to deal with those exponents if they're not negative, right? Having negative 2080 times L to the negative 2, just looking at that, I have to remember what that negative 2 actually means. It means that we're actually dividing by L squared, all that sort of stuff. Whereas I can just write it and now I can see what we're doing. And this is going to make the algebra easier because remember, now we're going to set this equal to 0. So this is our C prime of L. And so now we will, where's my number? Yep, there we go. Set C prime of L equal to 0. So we do 0 equals negative 2080 over L squared plus 17. So I'm going to go ahead and add the 2080 over L squared just to make everything positive. I could have subtracted the 17 and that would have been simpler to write, but it would have left both sides negative, which is fine, but I find if I can do something that reduces the number of negatives I'm tracking, that's always better. All right, and now we can do times L squared. Boop. So we'll do times L squared. So now we get 2080, 80 equals 17L squared. So of course we'll divide by 17. There was actually algebraically sort of a faster way to do this, but it sort of depends on a trick. And as often as possible, I try to avoid tricks. We can talk about those tricks, and I'm happy to, but in the middle of a problem is not really where I want to do it. All right, so if we do this division, it is a decimal. I think I'm going to leave it as 2080 over 17 for right now. That's fine. That's just a fraction. Equals L squared. And so, of course, we want to take a square root. Boom. Take a square root. The two there. And so our exact value, L is equal to the square root of 2080 over 17, which is approximately, and this is really what we care about here, right? Because this is where it is on the number line. This tells us actually about the length here, how many feet we're dealing with. This is 11.06 feet. That's excellent. Okay. And so what the problem actually wanted from us was the overall dimensions. Okay. So W, we'll remember, is 260 divided by L. So that's going to be approximately 23.51 feet. Does it make sense to us that the width is bigger than the length? We're trying to be economical here. So yeah, so like the picture I drew originally, right up here, definitely showed the length with the expensive side is longer. But if I thought about it for half a second, I probably would have realized, oh wait, the expensive side is going to have to be the shorter side. But that, keep that in mind when you're drawing your diagrams. Anything you didn't consider is not set in stone, right? The things you find mathematically might contradict your drawing simply because you didn't consider something as you were drawing it. And that's totally fine. Our drawing still served its purpose. Okay. So we can come up here how we want to answer this question now. And actually, I'll come back down here. So this is going to be, before we do this, before we get that approximation, let me show you how we're going to write this. So this is going to be, so this is 260 over the square root of 2080 over 17, right? But we're going to rewrite this. Honestly, you know what? Nope, you can input that just like this. That'll be fine. WebWork will take that just fine. So that's 23.51. Okay, there we go. So what we're going to do, we're going to, oops, sorry about that. Scrolled way far away. Sometimes the Miro board gets away from me a little bit. So our dimensions here are going to be, you're going to input the square root of 2080 over 17, like that. And for this other one, you're going to do, here's actually what I'd recommend you do. 260 divided by the square root of 2080 over 17 is the same thing as 260 times the square root of 17 over 2080. Right? And this is just, right, 260 over square root 2080 over 17 is equal to 260 times the square root of 17 over 2080. If you're dividing by a fraction, it's the same as multiplying by the reciprocal, even if that fraction is inside of a square root. So there's that. Excellent. Okay. And that takes us to the end here. I'm gonna sign out. Pass these problems back along to my student. I will. Oh, I need to update the website, but that's okay. I'll do that in a minute. I hope anybody who encounters this found it useful. I will be back tomorrow at 3:30 to 5. And there is a possibility of no stream on Thursday. I have kind of a full day, and I don't know how timing's gonna work out. I want it to, and I think it might, but I'm saying right now, I'm not sure where things are gonna land, and so I'll make a call one way or the other tomorrow by the end of tomorrow's stream. So yeah, wait to hear back from me, or I'll let you all know tomorrow about the stream on Thursday. But there definitely will be a stream tomorrow, 3:30 to 5. So I hope to see you there. But for now, have a great rest of your night, and I'll see you tomorrow afternoon.